You know, have you ever really stopped to think about how electricity gets to you? I mean, it's a journey that can cover hundreds of miles. And without this one incredible, kind of overlooked device, pretty much all of that energy would just fizzle out. So today, let's pull back the curtain on the silent giant that powers, well, everything. When you look at it, our world is basically stitched together by this huge web of power lines. You can think of the grid as the circulatory system of our modern life, right? It's pumping energy to every single corner of society. But, and this is a big but, sending that energy over these massive distances, well, that's a huge physics problem. So how do you solve that? How do you push all that power across the country without wasting it all? Well, the answer is actually in this really simple, super elegant, and incredibly powerful piece of engineering. It's the true unsung hero of our electrical world. And that hero is the transformer. What's so amazing is that it has zero moving parts, it's unbelievably durable, and it's literally the key that makes our entire power grid function. Its whole job is to change the voltage, either jacking it way up for long-distance travel or bringing it way down so it's safe to use in your home. All right, so here's what we're going to dive into. We'll look at why it's the grid's unsung hero, the clever physics behind what I call its magnetic handshake, what's actually going on inside that metal box, the tiny price it pays in energy loss, and all the different kinds of transformers you'll see out there. Okay, so here's the trick to sending electricity over long distances. Power companies jack up the voltage, way up. Think of it like water in a hose, right? High voltage is like high pressure. It lets you move the same amount of power with less current. And why does that matter? Well, lower current means less friction in the wires, which means way less energy is wasted as heat. Then, when it gets near your house, another transformer steps down that voltage to a safe level. Without this step-up, step-down process, the grid just wouldn't work, period. So the big question is, how does this box, with no moving parts, actually change the voltage? It's pretty cool, actually. It all comes down to a really fundamental principle of physics, a sort of invisible handshake between electricity and magnetism. Okay, the core concept is super simple. Whenever an electric current flows through a wire, it creates a magnetic field around that wire. Now, the really important part is that our grid uses alternating current, or AC. That means the electricity is constantly flipping back and forth. And because it's always changing, it creates a magnetic field that's also constantly changing. It's fluctuating. That fluctuation, that's the secret sauce. This whole process has a name, mutual induction. Here's how it works. First, that AC current flows into one coil, the primary coil, and creates that changing magnetic field we just talked about. Second, an iron core acts like a tunnel, guiding that magnetic field over to a second coil. And then third, and this is the cool part, that moving magnetic field induces a totally new electric current in the second coil. And the two coils never even touch. It's a perfect contactless energy transfer. It's like magic, but it's just physics. All right, so that's the principle. But what are the actual parts that make this all happen? Let's, pop the hood and take a look inside the box. It really just boils down to three essential parts. You've got the core, that's the highway for the magnetic field. Then you have the windings, which are the electrical roads. And finally, the insulating material, which keeps everything safe and from overheating. Let's break them down. So, the core. Think of it as that magnetic superhighway. It's made from a special kind of steel, but here's the clever bit. It's not one solid chunk. Instead, it's built from all these thin, insulated layers stacked together. And that design is genius because it stops these wasteful little energy whirlpools called eddy currents from forming. Without those layers, a solid core would just get super hot and waste a ton of power. Next up are the windings. These are the actual paths for the electricity. They're just coils of wire, usually copper because it's a great conductor, wrapped around that core. And here's the key. The number of turns in the first coil compared to the second coil is what decides if the voltage goes up or down. It's that simple. Now, in a lot of the bigger transformers, you'll find all these parts are literally swimming in a special kind of mineral oil. And this oil is a real workhorse. It does three jobs at once. It insulates all the high voltage bits, it keeps moisture from getting in, and maybe most importantly, it acts as a coolant, pulling heat away from that hardworking core and windings. Okay, so a transformer is an incredibly efficient machine. But nothing's perfect, right? No energy transfer is ever 100%. There's always a tiny price you have to pay, and that price is a little bit of lost energy. And when I say tiny, I mean it. Large transformers can be more than 99% efficient.
To put that in perspective for you, a regular car engine wastes something like 60% of its energy as heat. So yeah, the transformer is easily one of the most efficient machines humans have ever built. But still, where does that little missing 1% go?
Well, the losses basically fall into two buckets. The first is called core loss. This is just the energy it takes to keep magnetizing the core over and over. It's happening 24/7 as long as the transformer is turned on. The second is coil loss, or sometimes called load loss. This is basically just heat from the normal resistance in the copper wires. And this one changes. The more power you're using, the more heat you lose. Now, as you can probably imagine, not all transformers are created equal. They come in all sorts of shapes, sizes, and designs, and each one is built for a very specific job. Really, the biggest difference you'll find out there is how they're cooled. You've got the liquid-filled ones we've been talking about, the ones that use all that oil. And then you have what are called dry types, which, as the name suggests, just use air circulation and a sealed resin to get the job done. And yet, there are definite trade-offs between the two. The liquid-filled ones are generally more efficient, they last longer, and they can handle overloads better. But the dry types are usually seen as safer, especially for inside a building because, hey, there's no oil to leak or, catch fire. And I'm not kidding when I say these things are everywhere. I mean, from the absolute monsters you see in power substations all the way down to the little ones inside the power brick for your laptop. And then you have super specialized ones used in crazy high-tech stuff, like radar systems and even particle accelerators. They really are a foundational piece of our modern world. So next time you're out and you walk past a substation, or you just glance up and see that humble gray box on a utility pole, maybe you'll see it a little differently. Not just as some piece of equipment, but as that quiet, unseen giant, performing that elegant magnetic handshake millions of times a minute, all to power your world.
Like, share, and subscribe for appreciation and more content.